Okay. So hello everyone. We'll just get started in a second since some people are joining. So I'll just start in a minute or two. Okay, so I guess since a few of you have joined, so I guess we can get started. So once again, hello everyone. Welcome to the second session of the NPTEL Competitive Programming course. So, so just to reintroduce myself, I am Lakshay Saggi, the discrete maths TA for the problem solving TA for these Tuesday sessions, Tuesday evening sessions. So today's session will be again about the algorithms which were discussed in this week lectures like trouble sort and when you can reach a certain point or not, and so stuff like that. So I have some like 10 or 11 problems, so we'll be discussing those. And obviously if you guys have any doubts, feel free to ask those via chat. So I guess I'll just share my screen. So first, and if first of all, like if my voice is not clear or if you are not able to see the screen when I'll start sharing, please just message in the chat so that I can try to fix the problem. So yeah. So keeping that in mind, I guess we can get started. So let me just share my screen. Okay. So I hope the screen is visible to everyone. If if someone needs me to zoom in a bit more, then please tell me via chat. If it's clear, then maybe. Otherwise, I'll just assume that everyone can see the screen easily. So I'm just sharing the Word document in which I have the questions with me. So we'll be discussing these problems today. So since no one is saying anything in chat, I'll just assume that the screen is visible to everyone. So I guess then we can get started. So yeah. So so again, like last session, in this session also, I'll be assuming that you guys have already seen this week's video lectures, and because the problem statements are based on the video lectures only, and these statements can help you in the quiz also, the quiz which we have to submit every week. So yeah, I'll be assuming that you guys have gone through the lectures, and we'll be building problems from there onwards. So yeah. So some problems are from the ungraded assignment, so I'll discuss those also, so everyone can get an idea of how we came at the solution for those problems also. So yeah, like this first problem is from the ungraded assignment. So the first problem basically says that we are given an implementation of bubble sort. So we are given one implementation of bubble sort where there's a for loop for int I equals 0, I is less than n I plus plus. Then there's a flag, and we are just swapping the elements which are not in order one by one. So bubble sort has been discussed in the lectures, and its version of trouble sort was also discussed in the lectures. So yeah. So this is the bubble sorts code. And the problem statement is then asking which of the following statements is true. So there are like four options given to us. The worst case running time of the algorithm, basically the bubble sort algorithm, is order n square. Best case running time is order n square. The best case running time is order n, or none of the above. So so basically the question is about the worst and best case running times of this algorithm, the algorithm which has been given to us. So maybe everyone can take a quick look at the algorithm basically. So we are given an array's input, array as an input, n is the size of the array, and flag is just a Boolean variable. And now what we are doing is we are just looping from 0 to n, and we are keeping one flag variable which is true initially. And as soon as we encounter two out of place elements in the array, then we swap those elements and we put flag equals to false. And this is because this means that the array is not sorted. And if flag was true, then we stop our algorithm. If flag was false, then we continue in this loop. So would anyone like to answer this in chat? What would be the best case and the worst case running times? Okay, so Rahul is saying the answers are A, comma B. So Rahul is saying in chat that the worst case running time of the above algorithm is order n square, and the best case running time of the algorithm is also n square. So do you guys agree with Rahul's answer? Okay, so Anish is saying that Anish is saying in chat that A and C are correct. That the worst case running time is order n square, whereas the best case is order n. So yeah, actually, Anish, your answer is correct. So good job. So maybe I'll just discuss why is this the case. So basically the answer is this, that the worst case is order n square, whereas the best case is order n. So maybe we can discuss why this is true. So, so I'll just first write out the answer. Options A, comma C are correct. And why is this true? Uh, so it is easy to see. So basically what we are doing is we are making two for loops, right? So one for loop is goes from I goes from 0 to n, and j goes from 0 to n minus I minus 1. So if I was 0, so basically the inner for in the inner for so in the inner for loop, if I was 0, then this j goes to from 0 to n minus 1. If I was 1 in the outside for loop, then j goes from 0 to n minus 2. If I was 3, then j goes from 1 to 0 to n minus 3, and so on. So basically uh, we can see that for a given I, uh, so we'll be so while answering this sort of worst case running times argument, so what we need is we need an upper bound on the running time of of the algorithm, and we also need one example in which that upper bound is actually realized. Only then can we conclude that this is actually the worst case running time. That algorithm at least needs that the algorithm will always terminate in this time, and there exists an input which runs in this much time. There are two arguments which we need to give for discussing the worst case running time of an algorithm. So first I'll be trying to upper bound the running time. Maybe I should just mention it also. Upper bounding the running time. So how do we upper bound? So we can see that for a given I, the values of j go from 0 till uh, n minus I minus 2. Essentially, because as soon as j becomes to n equals I minus 1, then it does not go inside. So effectively, so the inside loop runs n minus I minus 1 times. So for a fixed value of I, the inside loop runs this times. So over all values of I, over all values of I, over all values of I, uh, the inside loop effectively runs the inside loop. So basically for a fixed value of I, the inside loop runs n minus I minus 1 times. So what we need is actually we'll need to sum over all values of I, because it is running one time when I was 0, another time when I was 1, another time when I was 2, and so on. So it effectively runs a total amount of uh, so summation n minus I minus 1 times. So I'll just, instead of writing the summation symbol, I'll have to maybe I have to find the symbol first. So maybe we can just write it like this. S- So it runs a total amount of n minus 1 plus. So when I was 0, the loop runs n minus, sorry for this. So the loop runs n minus 1 times. When I was 1, it runs n minus 2 times. When I was 3, and when I was 2, it runs n minus 3 times, and so on. And this goes on the fine, till I was equals to n. So something like that. Or basically when I was equal to n minus 1. So this will be the number of times, the total number of times the inside loop will run. So this sum is effectively nothing but, so this is just sum of first n minus 1 natural numbers, and this we learned in high school is equal to like n minus 1 times n divided by 2, which is something like an order of n square only. So we know that, so from this we conclude that the running time is upper bounded by order n square. But note that this does not mean that the worst case running time is order n square, because we could also say that the running time is upper bound by order n cube, order n to the power 4 or something like that. But we need to actually give an example also which realizes this running time of order n square. Otherwise, this does not mean anything, because upper bound could have been order n to the power 5 also, but we won't arrive at an example which takes n to the power 5 time. So here we have upper bounded by n square. We'll also need to give an example where this n square is realized. So an example which takes order n square time. So would anyone like to answer in chat? What kind of example here will take something like order n square time by looking at this algorithm? The example is not too hard to think of. So this is the algorithm, and we need to come up with an example which actually takes order n square time. So one can see that actually, all our efforts are going in this loop. So basically, we need that we have maximum number of swap operations. So yeah. So Rahul is saying in chat that a reverse sorted array. So yes, Rahul. So you're actually correct. So an array which is reverse sorted will actually take order n square time. So you can check this yourself also. So this array of, let's say, n comma n minus 1 comma n minus 2 till 1. So this is an array of length n, and you can actually see that this algorithm, this bubble sort algorithm, will take order n square time on this array. And just to give you an idea why is this the case, so first we'll come to this n and n minus 1. We'll have to swap these two as these are out of place. So this n minus 1 comes first, this n goes to second position. Similarly, another swap will take this n to the this n to this third position. Then another swap will take this n to the fourth position, and so on. So the first position, so this n actually needs to go to the last position, right? So it will need something like n swaps. Similarly, this n minus 1 needs something like n minus 1 swaps to go to the second last position. And n minus 2 needs something like n minus 2 swaps to n minus 3 swaps to go to the third last position, and so on. So this is why this will take something like an order n square time. So using these two arguments, we can actually conclude that the worst case running time is order n square. So we needed two arguments to establish the worst case running time. Similarly, we'll also need to lower bound the running time. So so while talking about the worst case, we needed to upper bound the running time, and we need to give an example which actually takes that much time. So similarly, for giving the best case running time, we'll need to lower bound a running time and give an example which realizes this lower bound. So so we'll need two arguments. First argument will be lower bounding the running time, and second argument will be an example which takes. So basically, we'll lower bound it by. So the actual answer is order n. So actually, we'll arrive at a lower bound of order n, and we'll also give an example which takes order n time. And many of you might think like why once again just reiterating that many of you might think like why can't just the example suffice? Like if I just give an example of order n square, if I just give an example of order n, why is this not correct? Just why do I need these upper and lower bounds also? So these are sort of needed because uh, you need to we need to sort of prove also that our examples are the extreme examples. Like the example which you use here is actually taking the worst running time. So this actually takes order n square time, but we also need to say that no example will take more time than this. Similarly, no example will take less time than order n. So that's why we need these upper and lower bounds. So I hope this sort of arguments are clear to everyone. So then maybe we can start. So for lower bounding the running time, so it will be a similar argument to how we upper bounded. So for this algorithm, it's easy to see that uh, the outside for loop actually runs for let's say at least n times, right? I goes from 0 to n. Uh, if flag is true, then this breaks also, uh, but it will actually so what I'm trying to say actually here is so for let's say the for I was initially 0 and we entered this loop. So as soon as we enter this loop, we see that this for loop, the second for loop of j, will go from j is equal to 0 to n minus 1. So something like that. And all of the statements of this for loop will get executed. So the inside loop will get executed at least order n times. And after that, maybe if flag was set to true, then then the outside I loop will break. And what this results in just is the inside loop running n times and outside loop running just one time. So something like a order n time. So what I'm trying to say is the inside loop will actually run at least order n. Uh, it will at least run from 0 to n. So that's why the inside loop will take at least order n time. So if I'm not making sense, maybe okay. So Rahul, you're saying that the inner loop breaks. So no, Rahul, actually the inner loop is not breaking here. The outer loop, the I equal to 0 loop is breaking. You can see the indentation of the code. Break, the if flag and break statement is with inside the outside loop, not the inside loop. So the outside loop is actually breaking. The inside loop will always get executed at least once. So I hope this is clear. So for lower bounding the running time, what we are trying to say is the inner loop of j will get executed at least once from j equals 0 to n minus 2. Okay. And hence the algorithm takes at least order n time. So the inner loop will get executed at least once when j goes from 0 to n minus 2. And so the algorithm will take at least order n time. And now an example which takes order n time. And now we also need to give an example which takes order n time. So in the same vein, actually, it's not too hard to see. The worst case example for bubble sort was this, where the array was actually reverse sorted. And the best case example, which will take this order n time, will be an array which is already sorted. So it is something like 1, 2, 3 till n. And why will this take something like an order n time only? You can see here that no swap. So this if condition of aj is greater than aj plus 1 uh, will never enter into this if condition, because this condition will never arise. So what happens is, in the initial execution only, the flag was true and it will never be set to false. So as soon as the flag is true, the whole outside loop will break. So we only enter once inside the outside loop, and after entering it, we just exit it afterwards. So that's why this just takes order n time for going through this inside loop. So, so maybe we can. So from the above two arguments, from this, we can conclude the worst case runtime is order n square. And from these two, the bottom two arguments, we can conclude that the best case runtime is something like an order n. So that's why options A and C are correct. Maybe I should write this below. Hence, options A, comma C are correct. And I can maybe underline this also. So yeah. So something like this. So if anyone has any doubts, you can ask in chat, or otherwise I'll just move on to the next question. So basically the A and C options are correct. So coming to the second question, I guess. So this is a common, so this figure is basically a common figure for problems 2 and 3. So this is also from the ungraded assignment only. So consider a modified version of the pseudocode discussed in the week's lecture, trouble sort. So we had discussed the trouble sort earlier. So so there was the lecture about trouble sort. So I'll just be assuming you know guys know what trouble sort is. So in this function, so in sort modify function, we have something like done equals false, while done is false, done is true, and then for I in range 0 to length of L minus 2, if L of I is greater than L of I plus 2, done is false, and swap Li comma Li plus 2. And in the end, we return L. So what this modified sort is doing is, again, it's very similar to trouble sort, but it has some changes. So we have something like we first set the done variable to false, and if done was false, then we set it to true, and then we search in the whole array. If we find two elements I and I plus 2 which are not sorted, which are not properly sorted, then we set the done to false again, and uh, the loop repeats. But if we find that all of these elements are already sorted, the ith and I plus 2th element, then actually we'll exit the loop. So the idea is quite similar to the initial trouble sort algorithm. So the only statement which has sort of changes this. So swap Li comma Li plus 2. So earlier what we were doing, if Li was greater than Li plus 2, we were actually reversing the whole array of Li comma Li plus 1 comma Li plus 2. But now we are just swapping the Li and Li plus 2th element. And actually, you can see that both these things will actually be same only. So this is actually doing the same thing as trouble sort. So this is actually same thing as trouble sort. And why is this the case? So you can see something like this from this figure. You can actually see that suppose we had something like Li was greater than Li plus 2. So let's just suppose that we have three elements, Li, then Li plus 1, then Li plus 2. And suppose we had encountered a condition where Li was actually greater than Li plus 2. So initially what we were doing was, in the initial trouble sort algorithm, we were reversing this whole subarray, right? So this actually becomes something like Li plus 2 comes first, then comes Li plus 1, and then comes Li. So this can act. So actually, what can be seen is um, this part to this part can also be realized by just swapping these li and li plus two variables. We don't need to reverse whole of this three length array, but we can just swap these li and li plus two, and it will just give the same answer. So this is li because this li plus one stays in place even if we reverse. So that's why this swapping li and li plus two or reversing the whole triplet of array is actually the same thing. So what this actually means is this problem is, so this sort modify is actually same as trouble sort only. So maybe I should just mention this also. So maybe I should mention this while writing the solution. Okay. So yeah. So first what we claim is so maybe not a claim, but we can just write it straightforward that it can be seen that the above code is same as trouble sort. As li as this to this can be achieved by reversing the three length subarray, as well as by just swapping li and li plus 2. So actually, this code is actually sort modify is actually same as the trouble sort only. So first of all, we established this. So now the question is actually asking true or false. The algorithm does not sort in ascending order in some cases. So if this code is actually same as trouble sort, and we learned about trouble sort in the lecture that trouble sort does not sort in ascending order in some cases. So I hope everyone has seen the lectures. So actually, this sorting technique is actually not correct. This will not always sort the elements in the ascending order. So since trouble sort does not sort in ascending order, in some cases, hence the above algorithm will also not sort. Will also not sort in ascending order in some cases. So actually, this statement that the algorithm does not sort is actually true. Hence, the statement is true. I hope this is clear to everyone. This was not too hard of a thing to see. So now we again come to the third question then. So the third question is saying, what is the worst case time complexity for this sort modify function? So for the sort modify, what is the worst case time complexity? So I just told you guys that the sort modify is actually same as trouble sort. And what was the worst case time complexity of trouble sort? So would anyone like to answer in chat? This was also discussed in this week's lecture only. And this is not too hard to see also. So yeah, right. So Rahul, Ram, Gopal, Nirud. So yes, guys, you are correct that order n square is actually the correct answer. So Ram Gopal, actually you have written something like a small o of n square. But the complexity will be the worst case complexity will actually be uh, big O of n square. So there's actually a distinction between small o and big O. So some of you guys might not know what does so what I'm trying to say is this this and these two terms are actually different. So these two things are actually different. So big O and small O are actually different. So what does big O actually mean in form? So you guys can look up the proper definition also. But what big O means is uh, that the complexity will be less than equal to n square, something like less than equal to symbol. Whereas what small o means is that it will be always less than n square, which is not the case because we can come up with examples where approximately order n square, it takes order n square time for this sort modifier to run. So just keep in mind, guys, that this big O notation and small o notation are actually different when you are talking about time complexity. So the worst case time complexity for this is big O of n square, not small o of n square. So just keep this in mind. Uh, so actually, as trouble sort takes order n square time, the above algorithm also has worst case complexity of order n square. So this is actually the correct answer. I'll just bold it. So yeah. Yeah, Ramgopal. So yeah, it is actually big O. So just a small point, but you guys should keep in mind since a lot of you might be computer science students and this big O and small O distinction makes a lot of difference. So yeah, just keep this in mind that this is big O of n square. So this was the third question. Then we come to, I guess, the fourth question. Maybe I'll just give some space. So again, another question for. So this is the last question, which uses the ungraded, which talks about ungraded assignments. Then I have some other questions also, other than the ungraded assignment. So yeah. So the question is something like this, that we are given an n cross n matrix and the task is to sort the matrix from bottom left to the top right across a subdiagonals in ascending order. So if you guys have already seen this question, so what we actually need to do is so if I hope everyone can see my cursor, right? So we are given an input matrix, and now we need to sort the values of this matrix in an order such that if we draw diagonals like this, so first diagonal is across this bottom left square, then then these two squares across which I'm moving my cursor, then these three squares, then these four squares, then these five squares, then these values, then this whole sequence should become sorted. So what actually means is this square, this bottom left square should have the least value, and then the second least value should be in the square above it, then in this square, and then so we are actually drawing diagonals like this. And in this order, the values should be increasing. So this should be the least value, then this should be second least, this should be third least, this should be fourth least, fifth least, sixth least, and so on. And you can actually see that this ordering is respected in this output, like -11, -10, -9, -8, -7, -6, -5, -4, -3, -2, and so on. So suppose this is the task which we need to, so this is something what we need to achieve. So we are given the square and we need to sort the square matrix in something like this fashion. So the brute force approach. So the problem was that we consider a brute force approach for this. And the approach is we iterate through the whole matrix and create a one-dimensional n square array. So what we actually do is we take all the matrix entries. Since we need to sort of sort all of these entries together, what we do is we create a single n square length array and put all of the values of this matrix into that array. So since there are n, this is an n cross n matrix, it will have n square entries. So our array will have n square entries. And now we just sort this array using quick sort in ascending order. And now as soon as we have sorted the array in ascending order, then what we can do is we can just create an output square and just start putting the values in the square in this order. Like the smallest value which we obtain through the ascending order will go here, then second smallest goes here, third smallest goes here. So essentially we start filling up this n cross n square in this manner. and this will result in our final in achieving a final goal. So I hope the algorithm is clear to everyone. So the key idea here is we iterate through the whole matrix and create one dimension n square array. And then, so what we are doing is we are actually sorting this array now. So we are sorting this one dimensional array, and then we are again outputting. And then what we are doing is we are again filling in the values of that array in another n cross n square matrix. So the sorting step of this n square array, we are saying we are doing it using quicksort. So, and now the problem asks us that what is the worst case time complexity for this problem, for this algorithm, the algorithm which we are talking about, that create an n square length array, then sort it using quicksort, and then fill this square up again. So I hope everyone knows what quicksort is. If you don't know, maybe you can ask me in chat. I'll just tell you a bit about it. So would anyone like to answer this question? What would be the answer to this? Okay, so I think there was a slight problem in this ungraded assignment. It was showing the answer as D order n to the power 4. And Ramgopal, you have also written this order n to the power 4. But how did you arrive at this, Ramgopal? I believe that this option D is incorrect, but I'll just be interested to know, like, what did you think that this is the. Okay, so Rahul is saying the answer is B. So order n to fill up the matrix and order n log n to sort. So yeah, actually, Rahul, I think the answer should be B, but like order n square to fill up the matrix and order n square log n square to sort, something like this. Because we have n square entry, so n will be actually replaced by n square. That's why the answer will be something like n square log. Okay, so Anirudh is saying order n square. So the correct answer according to me is actually answer B, n square log n. So maybe I can give you guys the reasoning also. So the steps taken by, so let's just discuss the steps taken by our algorithm. So let us discuss these steps in brief, something like this. So what they are doing is, so the first step is something like create n square length array, n square length array, sort the, so this is the high level summary of our algorithm. Sort the n square length array, fill the n cross n matrix using the sorted array, right? So this is essentially, so our whole algorithm can be divided into three basic blocks. First, we create an n square length single array, and then we sort this n square length array, and then we fill the n cross n matrix using this sorted array. So now what I claim is actually creating an n square length array just takes order n square time, because we need to just create an n square array and just fill up these values into that array. So yeah. So uh, so step A takes order n square time, as we just as we need to fill up the entries of the array using n cross n matrix. Then step B is actually, maybe I'll come to step B later. First, let's talk about step C. So step C again will take order n square time. So step C takes order n square time, as we need to fill up the n cross n matrix using the sorted array. So there are n square values. Filling up these n square values will take something like an n square time. And so we know that the algorithm will take at least n square time because of step A and step C. So the step B will also take some time, and the step B is actually to sort the n square length array. And note that the sorting an array can be done via multiple algorithms. So suppose we were actually given an n length array, then quicksort actually sorts the array in n log n time. So for step B, what I'm actually trying to say is we are sorting using quicksort. So there are different sorting techniques, but what we are employing is quicksort. So while talking about step B on an so using quicksort, what we can do is actually sort an n length array. Using quicksort, we can sort an n length array in order n log n time. So I hope everyone knows this fact that quicksort can be used to sort an array in n log n time. And now what we have is an n square length array. Since the length of array is n square, so quicksort on it will take how much time? On an n length array, it takes order n log n time. So on an n square length array, it will take something like just replacing this n by n square. It will take something like an n square log of n square time. And note that log of n square is nothing but 2 log n, and 2 is a constant, so it comes out in this order term. So the n square length array will be sorted in something like n square log n time. In order n square log n time. So I hope this is clear to everyone. So uh, I hope if this is not clear, then maybe you guys can ask me uh, in chat. So basically what I'm trying to say is the step B will actually take order n square log n time. Step A takes order n square time. Step C takes order n square time. So the whole algorithm will take basically the time taken by step A plus step B plus step C, which will come out to be order n square log n only. So the overall algorithm takes order n square log n time. So also just a note, so uh, hence option B is actually correct. So I just wanted to discuss this because I think there was some mistake in this ungraded assignment that the correct answer was showing as something like order n to the 4, which is not quite correct in my opinion. So yeah. So just a note for this. So here we were using quicksort, and quicksort sorts an n length array in n log n time. But we also discussed something like a bubble sort, right? So bubble for using bubble sort, what happens is for sorting an n length array, bubble sort takes something like an n square time. So if we use actually bubble sort, if we use bubble sort in step B, so what happens is bubble sort takes order n square time in an n length array. So for sorting an n square length array, it will take something like n square raised to the power 2, which will be n to the power 4. So if we use bubble sort, this step will take order n to the power 4 time. And so the overall algorithm will then take order n to the 4 time. Instead of. So I believe the answer to this has been given as order n to the power 4 for this question, which is I think because they were assuming we were using bubble sort. If you use bubble sort in step B instead of quick sort, then the algorithm will take order into the power 4 time instead. So I hope this is clear to everyone, like why will the algorithm then take into the power 4 time? If it is not clear, maybe you can ask me via chat or something. Otherwise, I'll just move on to the next question. Okay, so moving on to the next question then. So again, the next question what we have is a common question for the questions 5, 6, and 7. So 5, 6, and 7 will be using this question only. So it's again a question based on trouble sort. Maybe I'll just so the question is basically so first it just gives us the code of the trouble sort algorithm. So as we discussed, so that for using the trouble sort algorithm, let done is false, while not done we set done to true, and then for I equals 0 to length of L minus 2, we just do I plus plus, and if L of I is greater than L of I plus 2. So there's some issue in this code that guys this done is false and this swap operation you guys already know about trouble sort. So these should be inside the if condition. So these should have an indentation, but we have already you guys already know what trouble sort is, I'm assuming. So, yeah. And so here you can see also at that in this code we are using that swapping Li or Li plus 2 or reversing the sublist from Li to Li plus 2 because these two steps we discussed already that these two things are the same. Whether we swap Li and Li plus 2 or if we reverse the sublist from Li to Li plus 2. So yeah. So we are given the code of trouble sort and now the problem is asking us that consider the input list given as this. How many times swap operation will be performed between Li and Li plus 2? So the problem statement is asking us how many times will the swap operation will be performed in this input. The input is 5217348. So for this input, how many times? Uh, so just to it's okay. So maybe I should just put a note here also before discussing the answer for the viewers who might just view the PDF that uh the lines 7 and 8 of the code are inside the if condition of 6 line. Inside the if condition of line 6. So what I'm saying is these two lines are actually inside this if condition, as is the trouble sort. So yeah. So there is a typo here. So okay. Inside the if condition of that. Yeah. So so basically we have to run trouble sort on this input list and we have to tell how many times will the swap operation be performed in this. So Rahul is saying that the answer will be only once. Okay. So maybe uh, we can get started with this and just see whether what Rahul is saying is correct or not. So let's just start with the input list 5217348. Okay. So now what happens is, so we'll be considering the list one by one after every swap operation. So the initial list is something like this. So now while we are not done, the I pointer will move from 0 to length of L minus 2 and it will check how many times are we is the list not swapped. So it just comes, so as the I start from here, we are at 5 and we check the I plus 2th condition, which is 1. And we see that actually 5 is greater than 1. So we'll actually need to swap these two, right? 5 and 1 will need to be swapped because 5 is actually greater than 1 and we don't want it. We want to ensure that smaller value comes first. So for in the first swap operation, what happens is uh, 1 comes here, 1 and 5 actually get swapped. So it will be something like 7, 3, 4, 8. And after this, what happens is so we were at this I initially, and when we were at this I, what actually happened was we swapped these two values. So now then we come to the second I, and here we see that 2 is actually less than 7 already. So it is already okay with us. Then what happens is we come at this I and we see this 5 and 3, and we actually see that this 5 and 3 are also out of play. So we'll need to swap these two also. So I hope everyone is able to follow what I'm trying to say. So these 5 and 3 are also out of place. So we'll need to swap these two. So the 3 comes here and the 5 comes here. So something like this happens because these 5 and 3 were out of place. And now since our I variable was here, we have seen that this condition is okay now. So now we come to this 7 and we see that this 7 and 4 are here. And again, this 7 and 4 are out of order. So we'll need to again swap them. So this 7 gets replaced by 4, this 4 gets replaced by 7, right? So now we are initially at this position. So now we come to this fifth position then. And here we see that 5 is already greater than 8. So So we have traversed this list one times and we have write something like this. And now initially, since we had already swapped, the done variable is right now set to false. So we'll again enter this while loop and we'll again see whether we have arrived at the correct ordering or not. So what happens is we'll again enter from I equals 0 and we'll see that this condition that these two are in correct order. Then for the second I will see that these two are in the correct order. Then 3 and 5 are in correct order. Then 4 and 7 are also in correct order, and 5 and 8 are also in correct order. So what this means is that uh, the list. So basically, what this means is that the done variable. So we'll never enter this if condition here in the second time when we go from the start. So the done variable will never be set to false in this iteration of the loop. So what happens is the done is already true, and so now we exit the while loop. So so our code will now end, and this will be the return value. So this will be the answer of our code, and this is the sequence of swap operations. So how many swaps are being performed? So one swap was performed here, second was here, and third was here. So the answer is actually 3. Hence, the swap operation is performed 3 times. So I hope the answer is clear to everyone. So okay, so Rahul, I think I believe you have already got your mistake since you earlier typed that only once. And you have also mentioned in chat that it was your mistake. Okay, so if it's clear to everyone, maybe then we can move on to the next question. So, so maybe I'll just assume that it's clear and the answer is actually 3. So now, maybe we can go to the sixth question and its answer. So sixth question is again variant of trouble sort only, and maybe this was not okay. So what happens here is for which of the following input list the trouble sort algorithm will return a sorted list. So the problem just asks us that we are given five options, and in which of these options the trouble sort will return a sorted list, and in which of these options the trouble sort won't return a sorted list. So uh, I'll be assuming that you guys have seen the lectures, and in the lectures we sort of discussed. So it was discussed in the lectures that when does trouble sort return a sorted list and when does it not? So the key idea that was discussed there was that trouble sort only looks at odd indices separately and even indices separately and just sorts them independently. So what trouble sort actually does is, suppose this is the input list. So it looks at the list containing the terms 3, 1, 4, and 7 and sorts this list. And it also sorts the list of 2, 5, 8, and 9 and then just merges these lists together. So this is what trouble sort actually does. So what we need to actually show, what we actually need to ensure is that, so how do we check if the trouble sort will return a sorted list here? So we just see the option, and what we do is in the option we sort of sort the odd length in the odd lengths, the subarray which is made of odd indices and the subarray which is made of even indices, we sort these subarrays independently and then just combine these subarrays and just see then whether the final output is sorted or not. That is how we'll check for each of the options. So maybe I'll just mention this in a bit of detail as discussed in the lectures. Uh, Trouble sort just sorts the odd index subarrays and even index subarrays independently. So we'll check for every option. Sorting odd and so I'll just call these odd and even arrays, rather subarrays rather than odd index and even index subarray. Okay. So if sorting odd and even subarrays returns a sorted array, or maybe gives us a sorted array, then trouble sort will also return a sorted list. So I hope what I'm trying to say is clear to everyone. If it is not, you can ask me in chat. So we'll just go option by option here now. So the option A is something like this. So what we'll be doing is the recipes. We'll just be looking at odd indices and even indices separately. And I'm just assuming that indices start from zero. Like you can assume anything, but I'll be assuming indices start from zero. So let's consider this array. So even index sub array. What will be the even index sub array for this? So it will be the index 0, index 2, index 4, and index 6. So these terms will constitute the even index subarray. So the subarray will contain the terms 3, 1, 4, and 7. 3, 1, 4, and 7. And similarly, what will be the odd index subarray? Odd index subarray will be the index 1, index 3, index 5, and index 7. So it will be 2, 5, 8, and 9. So it will be something like 2, 5, 8, and 9. Okay, so we have made these as even indices and odd indices of arrays independently. And now what trouble sort is actually doing is sorting these independently. So what will be the sorted even index of array? So we can just sort this manually. We don't need to run the trouble sort algorithm. So what will be the sorted even index of array here? So it will be something like a 3147 will be something like a 1347. 1, 3, 4, 7. So I hope what I'm doing is clear to everyone. Again, just so what will be sorted odd index of array? It will be something like so this is actually in the correct order 2589. 2589. Okay. So the sorted even and odd indices of arrays are this. So final list returned by trouble sort. Okay. Yeah. So there was some final list returned by trouble sort will just be interweaving of these two lists, right? So even indices remain at even indices and odd indices remain at odd indices. So it will be like the first is the 0th index term. So even index term will be 1. So we'll be doing term by term. So this term will come at 0 index, this will come at first, this will come at second, this will come at third, this will come at fourth, this will come at 5, this at 6, and this at 7. So the final list returned to us will be something like a 1, comma 2, comma 3, comma 5, comma 4, comma 8, comma 7, comma 9. So we'll be doing this. So first the first even index term, then the first odd index term, then the second even index term, then the second odd index term, then that this term, then this term, and so. So I hope this is clear to everyone, like how the final list is returned by trouble sort. And we can actually see that in this option A, this array is not sorted. So this is not a sorted array. So now since the recipe is clear to everyone, I guess I'll be doing it a bit faster for other options. So now the second option is given to us is this option 3, 2, 1, 6, 5, 4, 7, 9. So again, I'll be dividing this into even index and odd index subarrays. Even index subarray, which will be something like so I'll be doing this a bit faster. So it will be 3, 1, 5, 7, and odd index subarray will be odd index subarray will be 2, 6, 4, 9, and so maybe I'll just copy these and maybe make changes to these. Yeah. So sorted even index subarray will be something like 1, 3, 5, 7. And the sorted odd index will be something like 2, 4, 6, 9. 2, 4, 6, 9. So the final answer will be 1, 2, then 3, then a 4, then a 5, then a 6, a 5, then a 6, and then a 7, and then a 9. So something like this. So we can see that this array is actually sorted. So, so I hope everyone is able to understand what I'm trying to do. So Rahul is saying in chat the answer is only B, and Anirudh is saying the answer is B and D. So maybe we'll just see all the options. So B actually we can see is actually sorted. So at least option B is correct. Maybe then we can go to option C. So maybe I can just copy the whole template of the option and just change the values. U H. So option C is something like 9, 7. This is option C. So yeah. So the even index of array is 9, 6, 4, 9, 6, 4, 2, and the odd index is 7, 5, 3, 1. 7, 5, 3, 1. And so the sorted even index will be something like 2, 4, 6, 9, 2, 4, 6, 9, and the sorted odd index will be 1, 3, 5, 7, 1, 3, 5, 7. And so the final sorted output, the output will be 2, 1, 4, 3, and then a 6, then a 5, then a 9, then a 7, which is not sorted. So option C is actually not correct. Now coming to option D. I'll just copy this template again. So the option D is now this option 1, 3, 2, 4, 5, 6. Yeah. So yeah. So even index of array here is something like a 1, 2, 1, 2, 5, 7, 1, 2, 5, 7, and the odd index is something like a 3, 4, 6, 8. 3, 4, 6, 8, 6, and then an 8. So sorted even index is something like a 1, 2, 5, 7 again. So this is already sorted, and this is also already sorted odd index. Right. Okay. I believe I did some. Yeah. So 1 3 1 2 5 7 and sort on this is something like a 3 4 6 8. Yeah. So the output here will be something like a 1 3 2 4, which we already see is not sorted. 1 3 2 4 5 6 7 8. So this is actually not sorted. So option D is actually not sorted. So whoever was saying option D, actually it is not sorted, according to me at least. Maybe we can come to option E also. Last option. So option E has this as the problem. And now let's just see the even index subarray here. So even index subarray will be something like a 7 5 3 1 7 5 3 1, and odd index will be a 8 6 4 2 8 6 4 2. So sorted values will be something like a 1 3 5 7 1 3 5 7, and here it will be 2 4 6 8. So the final return list will be 1 2 3 4 5 6 7 8. So this will actually be sorted. 1 2 3 4 5 6 7 8. So this will actually be sorted. So yeah. So yeah, Anirudh has also written in chat that the answer should be B and E. So Rahul, yeah, so B was correct, but E is also actually correct. So E is also an array which will be sorted by trouble sort. So the correct answers are just options B and E. So options B and E are correct. So Rahul, I hope it's clear to you like why E is clear, and maybe you have got your mistake. So then moving on to, I guess, the okay, it's clear, nice. So moving on to the seventh question, then so seventh question is a new definition which you guys might not have seen. So seventh question is asking us, or the defining us that what is a stable sort. So what does stable sort mean? That so if two elements have the same key value in the input, stable sort ensures that the element that appeared first in the input will also appear first in the output. So what does stable sort mean? Stable sort means that suppose we are given two elements that have the same key value. Suppose we are sorting a list of integers. Let's just ignore these triplets and some stuff. We are just sorting, let's say, a list of integers. And let's say, uh, or maybe let's just say, okay, so yeah, maybe just let's just say we are sorting some integers, and what we want to ensure is in the stables, what does stable sort mean? That the integer which comes first, let's say there were two fives in the array, and first I was at position like for the first five came earlier than the second five. Then in the sorted array also the first five should come earlier than the second five. So what I'm actually trying to say is that uh, so maybe I should define stable sort something like this. Defining, so stable sort will be something like this. Suppose I have given you this as an input, 1 4 uh, 1 6 5. Let's just say the problem is 1 6 5 5, and let's say I color these fives of as different colors. Let's say this is a red colored five, and this is a, so let's say all the numbers also have some colors, and this is a blue colored five. Maybe this color is very bad. I can choose some other color, uh, a purple color. Right. So let's just say we have these two fives, and now we want to sort of stable sort this array. So what does stable sort mean? So yeah, I should copy this first. So what does stable sort mean? So suppose I was given this initial array and I needed to sort this array. So one output will definitely be one. So the sorted output will definitely be 1556, right? But suppose I also want to preserve the colors of these fives. Like which five should appear? So one of these five was the white, purple colored five, and one of these was red colored five. So since both of these are fives, the sorted output won't change. Like even if we interchange these fives, one comes earlier or other comes earlier. So, but what stable sort says is that since red colored five was earlier in the input, the red colored five should also be earlier in the output also than the purple colored five. So the output should be something like this, that the red colored five should be this and the purple colored five should be here. So note that this is a stable sort. If the in the output the purple colored five was earlier and the red colored five was later, then that would not have been a stable sort. So this is the definition of stable sort. That suppose we are trying to so we are sort of trying to preserve the ordering of the inputs also along with the values. So coming back to the question, so now stable sort ensures that the element that appeared first in the input will also appear first in the sorted output. So this red 5 came earlier, so that's why red 5 came earlier in the than the value. Note that first we will be sorting by the values of these numbers only. Our primary criteria is this only, that which number is greater. That one is greater. So one is the least, that's why it comes first, and six is the greatest, that's why it comes last. This color or the input ordering criteria is only for the values on which we have a tie. So on these fives, we had a tie. Like we could have ensured that any five comes earlier, but while resolving ties, we take the ordering of input as the criteria for resolving the ties. That for resolving the tie between these two fives, we'll be putting the five which came earlier first. So something like this. So now the problem statement is that we have an input list of three-dimensional points, and we have to sort this in ascending order by the third coordinate. So all of these input points have third coordinate. So this is the third coordinate 1, 5, 1, 5, 2, and 0. So we need to sort of sort this array by the in ascending order of the third coordinate. So maybe instead of putting the options like this, which of the following corresponds to a stable sort of this input, maybe we can answer this ourselves. So yeah. What will be the stable sort of this input? So we need to actually answer what will be the stable sort on this input. So let's just say this was our input, and we have to basically sort these in increasing order of their z coordinates, right? So we need to see the z coordinates first. So one has this coordinate as 1, 5, 1, 5, 2, and 0. So we clearly see that 0 is the least and there is no tie breaking while we are writing this. So this zeros, the term which has 0 will come first. So this term will come first because this is the least value and there is no ties with this 0. And then we see in the remaining values, and the second least value after the 0 is 1. And this 1 occurs in these two inputs, the 681 and the 781. So there are ties, and how do we resolve the ties? As I said earlier, the ties are resolved using stable sort. So it would be something like, so this one comes earlier than this one. So that's why this comes first. 781 comes first, and then we arrive at this 681. I hope what I'm saying is making sense to everyone. If it is not, you can ask me in chat. So so this is 681. And now since we have resolved all the ones, now we arrive at 2. So there is only a unique 2 here. So this will be the next term 052. And then after this 2, so we have the next term which we have is a 5 in the sorted list. So note that we are ordering by the third coordinates. Maybe I should just mention it. Uh, the third coordinates are 1 5 1 5 2 0. So for this array, the third coordinates are these, and these when sorted, these when sorted become something like a 0, then a 1, then a 1, then a 2, then a 5, then a 5. So these are when they are sorted. And now we need to answer. So effectively, we need to output the whole triplet. So the triplet which contained a 0, so it comes first. Then there were two triplets which had a 1. So the triplet which had the 1 earlier will come first. So 781 comes first. Then comes the 681. And then we'll see which triplet had a 2. So this triplet had a 2, just a single 2. So the 052 comes next. Then two triplets had a 5. So the first triplet which has a 5 is this 375. So this will be the first which we'll be using. And after this, the second triplet is the 675. This will be the answer. So the stable sort is this. So this will be the answer. Yeah, so Anish, you're saying that there is no such question in your V2 assignment. So note that I'm not exactly solving your assignments, right? Because assignments have to be solved by you guys. But I'm just giving you guys some practice questions by which you can understand the concepts more. So maybe this question is not specific to this week's assignment, but yeah, this is also an important concept. The stable sorting concept is also an important concept when we are talking of sorting techniques. So that's why I believe this question is also relevant. So obviously we'll not be discussing exactly the assignment problem because those are your assignments. We'll be discussing some other problems also. So yeah. So this is the stable sort. So this is the answer for us. Yeah. So similarly, uh, so so now we come to the eighth question then. These questions are more for improving your understanding of these algorithms. And if you improve your understanding, naturally, sorry for that. So by improving your understanding, you can answer the assignment questions better. So even though these are not directly the assignment questions, but solving these questions will somewhat help you indirectly in solving the assignment questions. So yeah. So this is again a common question for the question 8 and 9. So the question is, so consider the problem, the meeting place cannot be changed. And this problem was discussed in the lecture video, right? And the input for the problem are being given as, so n equals to 4. So basically the number of friends is 4. And the x coordinates, the starting coordinates of the friends are 1, 4, 8, and 13. And the velocities of the friends are 1, 2, 2, and 3. I'm just assuming you guys are able to pass this input because uh, this is just the problem which has been discussed in the lectures also. And now the problem is asking us, is it possible to meet all four friends within 4 seconds? So, so maybe I should, is it possible for all four friends to meet within 4 seconds? So the problem is something like this, that we need to ask whether it is possible for all the four friends to meet within 4 seconds. So this is just a straightforward application of what we had discussed in the lectures. So what we want to ensure is, can all four friends have a common point within the 4 second period? So these are the maximum speeds of the friends and these are the initial coordinates. Uh, so, uh, okay. So after 4 seconds, the intervals in which the friends can be present are. So if you have seen the lectures, how we solve this problem, can all four friends meet within 4 seconds? So actually, we see the x value interval in which the friends can be a person can go within a 4 second period. So suppose this person was initially at point one, and he or she has a speed of one, so he can go like maximum of in 4 seconds he can go maximum to four to the right or four to the left. So it will be something like the interval will be from like 1 minus 4 to 1 plus 4. So it will be something like this. So the friends can be present in the intervals 1 minus 4 comma, maybe I should write it like this. So first friend will be present in this interval, which starts from 1 minus 4 into 1, and which goes to 1 plus 4 into 1. So why are there two square brackets? So this is the interval in which the first friend can be present after 4 seconds. And similarly, the second interval will be the value of the second friend. So second friend initially has a x value of 4. So initial value is 4. And maybe I should write down the formula also first. After t seconds, a person starting at position x with max speed v can be present anywhere in the interval x minus v times t till x plus v times t. So I hope this is clear to everyone. Or maybe like t times v. Let's keep the notations simple. Yeah. So a person at position x, starting position x with max speed v can be present anywhere in that interval x minus 3 times v to x plus 3 times v. I hope this is quite easy to see. So the first person, we first look at the first person. So initial position for him was like at position 1, and velocity and t is actually 4 because we are looking at the time after 4 seconds. So t was 4 and v was 1 for the first person. So he's present between the interval 1 minus 4 times 1 to 1 plus 4 times 1. Similarly, for second person, x was 4, t was again fixed at 4, t is again fixed at 4, and v is 2. So it's something like 4 times 4 minus 4 into 2, and this is 4 plus 4 into 2. And similarly, for the third person, it will be so initial starting position for the third position person is 8, and velocity is 2. So 4 times 2, and this is 4 times 2. And for the fourth person, the initial starting position is 13, and velocity is 3. So 1 minus 4 times 3 to this plus 4 times 3. So, so yeah, people are writing in chat that we can actually. Anish is saying, Rahul is saying, and Anirudh is saying that they can actually meet. The four friends can meet. So yeah, we'll just see. I believe this is the correct answer that they can meet. So we'll just see this uh, by resolving this answer also. So these intervals actually resolve to. So the first interval comes out to be 1 minus 4 into 1 is actually equal to minus 3. And 1 plus 4 into 1 is something like a 5. Then the second interval is 4 minus 4 times 2, which is minus 4. And this is plus 12. And here we have something like 8 minus 4 times 8, which is 0. And 8 plus 4 times 2, which 8 plus 8, which is 16. And for the fourth person, 13 minus 4 times 3 to 13 plus 4 times 3. So it is something like 13 minus 12, which is 1, and 13 plus 12, which is 25. So these are the four intervals in which these four friends can be present. So now we need to see whether these intervals have a common point. And the easiest way to check whether these have a common point was also discussed in the lectures, that consider the interval with the highest end. So consider the interval whose right hand side bound is the highest. So here this interval has the highest right hand side upper bound. And now what we actually need to, or the low, sorry, lowest right hand side upper bound, right hand side bound. So which has the lowest right hand side. So this interval has 25, this has 16, this has 12, and this has 5. So this has the lowest right hand side. So, and now what we need to ensure is basically the so it was in the lecture that for these intervals to have a common point, what we need to ensure is you can just draw this on a graph, or you can also just check whether the max of the max of the left hand sides should be less than equal to min of the right hand side, and only then the intervals will meet. So here the max of left hand sides is max of LIs is actually equal to the maximum of left hand sides is nothing but a 1. So -3, -4, 0, and 1. And min of right hand sides is nothing but a 5, 12, 16, 25 is nothing but a 5. So since min of Li is less than equal to, since max of Li is, since 1 is less than 5, so max of Li is less than min of Ri. So this means that since max of Li is less than min of Ri, less than equal to min of Ri, hence the four friends can meet within 4 seconds. So yeah, so this is the answer. So yeah, so many guys were saying that they can meet. So yeah, guys, you are actually correct. Good job that they can meet. And the one way to check this is you can just draw these intervals on a line, or maybe you can just check these max Li and min Ri values and just see whether this condition follows. This is an easier condition to check numerically, while drawing is not so applicable if you have a large number of intervals. So yeah. So yeah, so this is the answer, that the four friends can meet within 4 seconds. So now the next question is naturally, so they can meet within 4 seconds. Now we need to answer what is the minimum time uh, needed for all four of them to meet. So uh, we know that these friends can meet within 4 seconds, and now we need to check whether they can meet. So maybe this question I would say is mm, not that much interesting. So for this problem, maybe you guys can try. So this can be seen as sort of a maybe a homework problem for you guys or something. So for checking what is the minimum time needed for all four friends to meet at some point on the road. So for this, we sort of last time discussed in the lecture, it was discussed that maybe we can do a binary search on the time, right? That we have an upper bound that they can meet within 4 seconds, and we know that they won't meet in 0 seconds, right? So you can make an interval between 0 to 4 and perform a binary search and write a code and check whether these friends will meet at time 2, at time 3, and something like that. So it can sort of be done by writing a code. So maybe you guys can write a code for this. Maybe I'll just post. Uh, so I don't remember actually the correct answer. Maybe what we can do is instead of writing the code, we can change the question maybe a bit, and we can have some options. What is the minimum time of the given options needed for all four friends to meet at some point. So let's just say we make up some options. Let's say 3.5, 3, 4, and let's say something like a 2.5. So we are given these four options. And now what we need to find out is what is the minimum time of the given option needed for all four friends to meet at some point. So basically, out of these four options, we need to check the minimum time at which these four friends can meet. So I hope the question is clear. Maybe this is a better question for these sort of sessions because we are not writing any code for any problem. So yeah. So so we need to find the minimum time. So minimum time is obviously 2.5 here, but we are not sure if two if at 2.5 seconds all four friends would actually be able to meet also. So what the question is asking us is out of these four options, what is the minimum time at which the four friends will meet? So we already know that they will meet at 4 seconds, right? So 4 is one possible option, but we need to check the other options whether it is possible to meet at lower times also. So let's just start with naturally with the smallest value. Uh, so check for all options if it is feasible for all to meet. So starting with, so natural ways to first start with the lowest value, which is like 2.5, because if we are not able to meet here, or let's say if we are able to meet here, then this will just be the answer. And it will save us the effort of calculating for all these options also. So starting with the lowest value, t equals to 2.5, what we get is the after 2.5 seconds. So the intervals in which the friends can be present will be something like this. Uh, Maybe I can copy paste this whole line. The intervals in which friends can be present are something like this: 1 minus 2.5 times 1 plus 2.5. Similarly, 4 minus 2.5 to 5 here. Similarly, 2.5 here, 2.5 here, 2.5 here, and 2.5 here. So yeah, so maybe we can do the calculations a bit faster now, since we had already solved this sort of question earlier. So this will come out to be, so I'll just be resolving this. This will come out to be minus 1.5, and this will come out to be 3.5. This will come out to be 2.5 times 2 is 5, so it will come out to be minus 1. You guys can also try this while I'm also calculating this. So this will be 8 minus 2.5 times 2. So this will be something like a 3. And this will be something like a 30. And similarly, here we'll have something like a 7.5. 13 minus 7.5 is 5.5. And this will be 7.5. So it will be like a 20.5. So again, these are the four intervals, and now we know the value, what will be the, and now we need to check what will be the values of max size and min size. So max of Li will be something like minus 1.5, minus 1, 3, and 5.5 will be 5.5. Whereas the min of Ri will be 3.5, 9, 13, and 20.5. So min will be something like a 3.5. So we sort of see that max of Li is actually greater than min of Ri. So here, since max of Li is greater than min of Ri, hence the four friends cannot meet within 2.5 seconds. So for 2.5 seconds, we know that the friends cannot meet. So naturally, we'll go to the next option, which is 3. So I hope everyone is able to follow what I'm trying to do here. I'm just doing the same calculations now for these options also. So this is more of an just a repetition of the argument with different calculations. But yeah. So now we start with option, another option, which is after 3 seconds. T equals 3. After 3 seconds, the intervals will be something like this, this, this. So I'll just replace all these 2.5 by 3 so that it's easier for us to perform the calculation now. So read with the values, and now 1 minus 3 times 1 will be nothing but a minus 2, and 1 plus 3 times 1 will be nothing but a 4. Right. Similarly, 4 minus 3 times 2 will be nothing but a minus 2, and this will be nothing but a 10. Similarly, this 3 will actually go down to 2. This will become 14. This will go down to 4.5, or sorry, maybe I did some mistake here. Let me just say. So it goes down to minus 2, it goes up to 4. This goes down to minus 2, this goes up to 10. Then this goes down to 2, this goes to 14. And here it will be something like a 4. And this will be something like a 20. Right? So max of LIs here will be something like a minus 2, minus 2, 2, and 4. So max will be something like a 4. And the min of RIs will be again 4, 10, 14, 22. So it will be something like a 4. So min of Ri is also actually equal to 4. So here we see that this is the 4 which I'm talking about. So max of Li is actually equal to min of Ri. So if those are equal, then also the friends can meet. And there will be a unique meeting point, which will be actually at the fourth coordinate. So all 4 friends can meet actually when they are equal also, and that will be at this coordinate 4. Can meet within 3 seconds. So they could not meet at 2.5. They can meet at 3. So they can obviously meet at 3.5 and 4. So the minimum time is actually 3 seconds. Hence, option B is correct. So I hope everyone was able to get what I was trying to do here. So if you have any doubts, you can ask me in chat, or otherwise I'll just move on to the next question then. Okay, I guess I can go on to the next question. Okay, so maybe so we have 2 questions and we have sort of 20 minutes left. What I can do is mm, maybe we can remove this 10th question, because this sort of question is already present in the assignments, and like this is not too hard. So yeah, so maybe we can remove this 10th question, and yeah, we can discuss this question instead. The last question, which is related to magic ship, because I believe this sort of question is present in assignments also, and yeah. So let's see the question. So the problem asks us that consider the magic ship problem discussed in the video lectures. So yeah, magic ship problem, everyone must have already seen. If you have already seen the video lecture, you must know what the magic ship problem is. So now given the weather forecast, so weather forecast is given to us as UDDLRLU, and the ship starts at point 0, 0. How many days will it take for the ship to reach the point 3, 2? So the problem is asking us in how many days will the ship reach the point. So let's say we want to find the minimum number of days in which the ship can reach the point 3, 2. So yeah, and we are starting at this point 0, 0. So again, we want to find out the minimum number of days. So this is also something along which this is also sort of problem which has been discussed in the lectures. So yeah, this is also has a very straightforward technique, but I'll just use this technique because there is an assignment problem related to this sort of question also. So yeah. So we are given this forecast that the 7 day so this is the 7 day forecast. And now what we want is we are starting at 0, comma 0, and we need to reach this point 3, comma 2. And so we need to see how many days will it take for us to reach there. So in this sort of problem again, we want to find the minimum number of days. How many days? Or maybe we can just say like in how many days can we reach? So we can reach in. Yeah, okay. Maybe we can just take this. How many days will it take for the ship to reach the point 3, comma 2? So will it take 5 days, 6 days, 7 days, or 8 days? So note that if we take 6 days, let's say, then we can also take 7 and 8 days. So if we are able to reach the destination in 6 days, then we can reach the destination in 7 as well as 8 days also. Because as was discussed in the lectures also, that we can move the ship in the opposite direction of the wind. So yeah. So we essentially need to find the minimum of all these options at which we can reach the destination. So let's just try with mm, let's start with 5 days. So can we reach the destination in 5 days? So so to check whether we can reach the destination in 5 days, what we do is, as was discussed in the lectures, we just take the 5 days of weather forecast here. So the 5 days forecast is something like a UDD-LR. So 5 days forecast is equal to nothing but UDD-LR. So So why the so what we do in this sort of problem is, as was discussed in the lecture, we take the effect of the wind independently, and then we see whether we can reach independently. So we take the contribution of the wind first, and then we take our contribution and check whether our own contribution can be done within 5 days or something like that. So so the contribution. So the wind alone actually the wind alone takes us to, so if we started from 0, comma 0, and if we do nothing, the wind will take us to something like a UDD-LR. So it will be something like we'll first go to 1, 0, from 0, 0, we'll first go to 1, 0, then we'll come down after this to 0, 0, then we go to minus 1, 0, then this will take us to minus 1, comma minus 1, and then this will take us back to minus 1, comma 0. So after this whole fiasco is over, okay, sorry. I Yeah. So we'll be net one box down here because will be down by one axis, because this down will these U and D will be negated, these L and R will be negated. Only this D contributes, and this D contributes a -1 to the y coordinate. So the wind alone takes us to 0, comma -1. And what happens because of this is, so we call this point, let's say x3, comma y3. X3, comma y3 is equals to this. And now we need to sort of find as was discussed in the lectures, we need to find the Manhattan distance of x2, comma y2 from x3, comma y3. So x2, comma y2 from x3, comma y3. And this is nothing but the the absolute difference between the x values and the absolute difference between the y values. So x2, comma y2 is x value is 3 and x3 is 0. So it will be something like a 3 minus 0. And here we have something like y2 is 2 and y3 is -1. So it will be something like a 2 minus of -1. So note that there will be two minuses. So this will effectively come down to 3, and this will also come down to 3, which is 3 plus. So 3 plus 3, which is equal to 6. So Manhattan distance is actually 6. So, but we only have something like 5 days, right? So we are trying out the option for 5 days. So in 5 days, we can only move maximum distance of 5 and not 6. So actually, we won't be able to go there. Since we only have 5 days, we can't cover a distance of 6. Hence, destination can't be reached in 5 days. So I hope this sort of argument is clear to everyone that, okay, so Anirudh is saying the answer is C. Maybe we can just check also. So 5 days is absolutely not correct, that we can't cover the destination. Maybe let's go with maybe this was option A. So option A is not correct. Let's go with option B then, whether we can reach the destination in 6 days or not. So we'll just copying this whole format. So can we reach the destination in 6 days? And the 6 days where the forecast is UDD, LR, and then another L. UDD, LRL. So if we are doing this, so UDD, LR took us to something like 0, comma minus 1, and then another L will take us to something like a minus 1, comma minus 1. So Manhattan distance will be something like a 3 of 3 minus of minus 1 plus 2 minus of minus 1, which will be something like a 4 plus 3, which will actually be equal to 7. So, and now we only had 6 days. So, and we had a Manhattan distance of 7. So I hope you guys are able to follow this. So we can't actually uh, cover a distance of 7. So the destination can't be reached in 6 days either. Okay, so we are getting somewhere that the destination can't be reached in 5 days as well as 6 days. Maybe let's try option C, which is 7 days, which is what you guys are claiming that is actually correct. So can we reach the destination in 7 days? So 7 days forecast is something like so 7 days forecast is UDD, LRL, UDD, LRL, and then another U, right? So this UDD, LRLL took us to minus 1, comma minus 1, and then another U will take us back to minus 1, comma 0, right? So Manhattan distance from here will be something like a 3 minus of minus 1 plus 2 minus 0. So this will be something like a 4 plus 2, which is nothing but 6. So Manhattan distance of x2, y2 from x3, y3 will be 6. And now we have, and now since we have 7 days, because we are starting with 7, we can cover a distance of 6. So the destination can be actually reached in 7 days. So destination can be reached in 7 days. And now we try the 8 days option. So for 8 days, it's easy to see that since we are able to reach in 7 days, since we are able to reach in 7 days, we can also reach in 8 days, right? So I hope this is clear. This is the main part of the argument that in 7 days we were able to reach. And the basic outline of these sort of problem is very easy to see that just see the wind, how much the wind takes us alone, then just see the Manhattan distance of that point to the destination, and then just check whether the Manhattan distance is less than equal to the number of days which are given to us. So this is the de facto method for solving this problem. So yeah, there is some problem in the assignment also, which is similar to this. So yeah, so we can reach in 7 days. So if we are able to reach in 7, we can also reach in 8 days. So option C and D are actually correct. Hence, option C, comma D are correct because we can reach in 7 days as well as 8 days. So yeah. This is the correct answer. So if it was asked what is the minimum number of days in which we can reach, then the answer would have been just C. But yeah, C and D also make sense. This is more of a technical point, but yeah. So good job, Anirudh. You wrote C in the chat also. So yeah, you were correct. Okay. So yeah, so this was the 10th question and we have solved this. So yeah, so I have no more questions. So I guess this wraps up the today's problem from my side, guys. So since we also have something like 10 minutes left, so if you have some short doubts or queries which you would like me to address, then maybe you can ask me via chat. Or if there are no doubts or like no comments, then I guess we can close the session also. So if you guys have any doubts, any comments, any remarks, anything, you can tell me. Otherwise, okay, so I guess since no one is responding with anything in the chat, I'll just assume that uh, I'll just assume that no one has any doubts. So yeah, uh, thank you, Rahul, for your thanks. So yeah, so I guess I'll just be stopping the recording, stop sharing my screen, and I'll just close the session since no one has any doubts. So hopefully we'll see you guys next week also, same time, Tuesday, 6 to 8 p.m. So yeah, thanks for attending, guys, and hopefully we'll see you next time. Goodbye.